Hello everyone, this is Mr. Appel, and today we're going to continue with counting. We're going to just step it up a notch. Yesterday we looked at the fundamental counting principle. Now we're going to look at some variations on that, namely permutations and combinations, and understanding the differences between the two. So let's take a look. Wow, that's a lot of information. All right, let's try to break this down. So permutations are situations in which order is important. Order matters. So the order that things are in matters. So for example, if you're finishing a race and there's a bunch of people in the race, and if I'm first and you're second, that's a different result than if you're first and I'm second. So the order is important. And there are some situations where that matters, and there are other situations where it doesn't, and that's kind of what we're going to look at today. When order matters, it's called a permutation. Permuting, like rearranging things. Sometimes we rearrange books on a shelf. We'll look at some different examples in just a moment. Generally speaking, with permutations, you can use the fundamental counting principle. You can use the counting principle like what we did yesterday. But in a lot of situations, this is just easier and more efficient to get to an answer. And this formula, NPR, not National Public Radio, but NPR, that's P stands for permutations, and the N is the number of things there are to choose from, and then you're picking R of them at a time. And I'll explain that in an example in just a second, and I think that'll make more sense, but you should be familiar with this formula. Although it is in your calculator, so you will often be able to just type it into your calculator, but you should know this formula. Repetition is not allowed. That's big in permutations because, again, if I'm batting first in a batting order, I can't also be batting second. If I finish first in a race, I can't also finish second. So that's what we're looking at with permutations, and let's take a look at an example. I think it'll make a little more sense if you're confused. So here's an example. I've got 13 people on my baseball team, and I need to make a 9-person batting order. And me being a math nerd that I am, I'm interested in how many possible batting orders can I make. So some things to think about here in terms of determining what the situation is, that this is in fact permutations. Can a person bat more than once in the batting order? Absolutely not. If you don't know baseball, that's a fact. If you're batting second, you can't also bat fifth. Everybody's in a different spot. And does the order matter? Well, sure. If I'm batting first, like I mentioned earlier, that's different than if I'm batting second, so order matters. So this is permutations. So I'm going to show you several different ways you could do this calculation. We could do it the way we did it yesterday with fundamental counting principle. I've got a 9-person order, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And I ask myself, how many people could bat first? Well, I have 13 to choose from to bat first. After I choose one, there's 12 left to be second, and then 11, and then 10, and 9, and 8, and 7, and 6, and 5. Yuck, that's kind of a lot of writing. Or I can use NPR. N being the number of things there are to choose from, which in this case is 13. R being the number of people I'm choosing from that 13. So I'm choosing 9 out of the 13, so 13P9. So if I use that formula, which you should have written down, but it's back on this page, it's N factorial over N minus R factorial. So that would be 13 factorial over 13 minus 9 factorial, which is 13 factorial over, wow, that's really horrible to read. I'm sorry, let me fix that. Try that again. So that would be 13 factorial over 4 factorial. Now you might be saying this doesn't look exactly like that, but what's kind of cool about factorials is if you picture what this looks like, it's 13 times 12 times 11 times 10 times 9 times 8 times 7, blah, 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 down to 1. This down here is 4 times 3 times 2 times 1. So I'm not going to write it all out, but if you can picture all that written out, 13 multiplied all the way down to 1, and this 4 times 3 times 2 times 1, some stuff cancels out, namely the 4s, the 3s, the 2s, and the 1s. And what does that leave you with? It leaves you with this. But this is much easier to calculate, much easier to type into your calculator than this big long thing is. So you can see this is an example where using this formula is handy. And I want to show you what that looks like on the calculator. We'll bring up our calculator here. So so we could type in 13 factorial over 4 factorial the way that we did yesterday. But you can also use, there's actually NPR, the formula is built into the calculator. So I can do 13, and then I can go to the math, probability, and notice there's NPR. So 13, NPR 9, and I can put that in, and there is my answer, which is the same thing if I just did 13 math probability factorial divided by 4 math probability factorial. And we get the same answer. Just a little bit more efficient, and something here that you can do in, like I said, in a variety of different ways. Okay, so that's permutations. Hooray. Okay, next up is combinations. So combinations are situations where the order does not matter, where the order doesn't matter. And we'll talk about some examples of that. But for example, I'll give you one. If I've got 12 players on my basketball team, and I want to pick 5 of them to start. If I pick Joe first and Phil second, and then 3 other people, or if I pick Phil first and Joe second, doesn't matter. It's the same 5 people that are playing. So the order doesn't matter. It's just how many different 5-player teams could I put out on that floor? So that would be a question we might ask. So that's combinations instead of permutations. And again, the order doesn't matter. That's the big difference. And notice the formula for NCR, which is combinations, looks similar, except we also have this R factorial down here. And what that does is it eliminates counting order arrangement. So, and that may not make a lot of sense, but it basically accounts for all the different ways that the things you choose could be rearranged. And if that, I know that wasn't totally clear, we can talk more about it in class, but that's kind of what happens in this formula. Okay, let's look at an example, and I think we'll clear things up, because that even sounded confusing to me the way I just said it. Okay, let's look at a couple examples. So if I wanted to buy 3 songs off the top 10 list in iTunes, I'm interested in how many possible ways that could happen. Well, again, if I'm buying 3 songs, it doesn't really matter if I buy, Radioactive first and What Did the Fox Say second, or What Did the Fox Say first and Radioactive second. It doesn't really matter. It's the same songs. So the order doesn't matter. So this is combinations. So there are 10 songs to choose from, and I'm choosing 3 at a time. So this is 10C3. Doing that using the formula, that's 10 factorial over R, which is 3 factorial, times n minus R, which is 10 minus 3, which is 7 factorial. And that's what you would put into your calculator. Let's see what that comes out to. So we've got 10 factorial divided by, and remember this came up yesterday, you need to put the denominator in parentheses so it knows you're dividing the whole by 3 factorial times 7 factorial. I know it's a little bit tedious to type in those factorials on these calculators. It's actually easier on a scientific, but you'll get pretty comfortable at it. And there's my answer, 120. So that's 120 different possibilities. And again, I just want to show you that an easier way to do that using a graphing calculator and your scientific is to do 10 math probability, and now we have NCR there. So 10 NCR 3. And we get the same answer. Just a little bit easier way to type it. Okay. I've got another example there. Well, let's do that really quick. So 5 card hands out of a 52 card deck. So that's 52C5, 52C5. And again, that's if I'm picking 5 cards out of a deck, it doesn't matter what order I picked the cards. If I've got 4 aces and a king, I've got 4 aces and a king. It doesn't matter if I got the king first or one of the aces first or whatever. So again, quickly, that would be 52 math, probability, NCR, which is 3. So 52 NCR 5 is the way you type that in your calculator. And I see that there are 2,598,960 different 5-card hands in a deck. That's all for today. Thanks.